Welcome to Lesson 3, Forces of Flight and Aerodynamics. So a glider stays aloft and it maneuvers by interacting with the air that it's moving through. That generates forces on the glider, and understanding what generates these various forces will help you in your ability to manipulate the controls to control those forces so that you can make the glider do what you want it to do. In this lesson, we'll start by talking about the forces of, of flight, the forces that are generated on a glider. We'll talk about how a wing creates lift. We'll focus mainly on the wing. Uh, the vertical tail and horizontal tail also create forces using basically the uh, same principles, but we'll focus mainly on the wing. Talk about what determines the magnitude of that force. And then we'll talk about two types of drag. Induced drag is the drag that's directly related to producing lift. Parasite drag is the drag that's produced for other reasons. Um, Finally, we'll talk about stalls and spins. So some of you may not have had a physics class yet, and others may have had a physics class many years ago and don't remember everything. So before I get into the discussion of that will require some physics concepts, I want to review those concepts here. First off, let's talk about some of the difference between scalar quantities and vector quantities. Some physical quantities are measured with a single number. For example, temperature or air pressure. These quantities are called scalars. Other quantities have both a magnitude and they have a direction. Some examples of this would be force or acceleration. These type of quantities are called vectors. When we work with vector quantities, oftentimes it's convenient to put a coordinate system in place and express the components of that vector in different coordinate directions. So this situation, we've put an XY coordinate axis, and this vector A can be broken down into components in the X direction and in the Y direction. So objects in motion tend to stay in motion, and they stay in motion at the same speed and in the same direction unless they are acted on by an outside force. It is those outside forces acting on the glider that we will be talking about a lot in this course. So a force in the same direction that the object's moving speeds it up. A force in the opposite direction slows it down. And a force that's perpendicular to the direction that the object's moving changes its direction that it's moving, but does not change the speed. Force equals mass times acceleration. Mass, for our purposes, is basically the same as weight, since we don't worry about operating on different planets or anything. Um, so in other words, it takes more force to change the speed or the direction of a heavy object than what it takes to change the speed or direction of a light object. Or thinking of it another way, a particular force acting on a heavy object will change its speed or direction only a little, whereas acting on a light object will change its speed or direction a lot. If an object's moving fast, then it takes more force to change that object's direction of motion by a given angle. So an object is when you're going north on the highway and you want to change to east over a given period of time, like say you're taking an exit ramp, That will, at highway speed, that takes a lot of side force on your car. In the other circumstance, say you're in a parking lot and you need to make a 90-degree turn into a parking space, it doesn't take a lot of force on your car to change its direction of motion in that situation. For every action, there is an equal and opposite reaction. In other words, if you exert a force on something in a particular direction, that object will exert a force on you, called a reaction force, that will be in the opposite direction. Some examples that you may be familiar with from your other experiences is if you fire a gun, that gun exerts a force on the bullet to accelerate the bullet. The bullet then accelerates a force on the gun, pushing the gun back in the opposite direction, which the gun transmits on to you on your shoulder. Things don't have to actually be changing speed for there to be reaction forces. When you're just standing on the floor is exerting an upward force on you that's counteracting gravity and keeping you from falling down. You're applying a force on the floor in a downward direction in that situation. Even though this is a glider ground school, I'm going to start my discussion of forces of flight with the situation of an airplane in straight and level flight. There are four forces acting on that airplane. There's weight caused by gravity, which always acts straight down towards the ground. There's lift coming primarily from the wing, which in most flight conditions will be acting upward and counteracting the weight. Drag, which is caused by air flowing over all sorts of the parts of the airplane, tending to make the airplane slow down, and thrust generated by the airplane's power plant, which would tend to make it speed up. So in this straight and level steady state condition, the weight is equal to the lift. So the aircraft stays level. If the lift exceeded the weight, then the flight path would tend to bend upwards so that the aircraft would transition into a climbing situation. If the weight was higher than the lift, then the flight path would tend to bend downwards and transition into a descent. The thrust, if the thrust exceeds the drag, then the aircraft would tend to speed up. If the drag exceeds the thrust, then the aircraft would tend to slow down. But when they're equal to each other, then the aircraft is in a steady state. But now when we talk about a glider, this thrust force doesn't exist. We don't have a power plant that can create it. So the thrust is equal to 0, but even though the drag is very low in gliders compared to other type of aircraft, it's not 0. It's some positive number. So how can this work? So in a glider, we aren't moving straight forward through the air around us. We're always actually in a slight descent relative to the air that is around us. So we have to think of this concept called the relative wind, the direction that the air we are encountering is coming at us from. The lift and the drag their direction is measured relative to that relative wind. And since we are descending a little bit, that relative wind is angled down a little bit. Our lift vector is angled forward a little bit, and our drag vector is angled upward a little bit. The lift vector has X and Y components, as does the drag vector. And this forward component of the lift vector is what counteracts this rearward horizontal component of the drag vector. L sub x is equal to d sub x. That's what keeps us at steady speed. The y component of the lift vector is what counteracts our weight. This d sub y, the vertical component of the drag, it's tiny, and we can kind of neglect that in the circumstances that we normally operate a glider. If we were talking about a dive bomber or something like that, then it wouldn't be appropriate to neglect that component anymore. But for the way gliders work, we can kind of ignore that component. The glide ratio, which the definition of it is how far forward you move for how much you sink, is equal to you can work out the geometry on the picture. You can see that angle is the same as this angle here, and the glide ratio would be equal to the lift, the L sub y over L sub x. It's also equal to the lift over the drag. And that will be an important concept to remember, that the glide ratio is always equal to the ratio of the lift to the drag. Before getting into the explanation of lift, I need to define a few terms here. First term is the concept of a chord line. So this is a imaginary line that runs through the trailing edge of the wing and the leading edge of the wing. And the angle of incidence is the angle between the chord line and the longitudinal axis of the glider. So the angle of incidence is set by the aircraft designer. We don't manipulate it as a pilot, except that some gliders have flaps on the trailing edge, which allow you to manipulate the chord line a little bit. And the manipulating the ailerons change the chord line at the wingtip area a little bit. The angle of attack is the angle between the chord line and the relative wind. This we do manipulate. As pilots, we manipulate this by manipulating the elevator such that we get the angle of attack that we need for the given flight condition. So there are two different ways of explaining lift that you may hear in different situations. One is Newton's second law, and the other is Bernoulli's principle. Sometimes you'll hear people get into debates about which one's right. They're both right. There's nothing incompatible with the two. They explain it in just explaining the same thing in different ways. I find that the second law explanation is more intuitive, but other people may find the Bernoulli's explanation more intuitive. So I'm going to present both of them here, and I'm going to start with the second law explanation of lift. So the wing deflects the air as it moves over. We'll notice that this first red arrow at the front reflects the relative wind. That's the angle the air is coming at and encountering the wing at. The second red arrow reflects the direction that the air is moving as it moves away from the wing. And they're different direction. They're about the same speed, but they're different direction. The wing deflects, changes the angle. In order to change the angle of the air, it has to exert a force on that air. So this blue vector here represents the force that the wing is exerting on the air. Since there's an equal and opposite reaction, the air is exerting a force on the wing in this direction represented by this upward blue arrow. This reaction force it's close to being perpendicular to this relative wind, but it's not exactly equal to it. It's kind of halfway between the oncoming and the offgoing. So it's tilted back a little bit. The perpendicular component is the lift, because lift is always defined to be the amount of force relative to the relative wind. The little bit of this blue reaction force that is parallel to the oncoming wind, that's called the induced drag. We'll talk about that more later. So what determines the magnitude of the lift when we think about it in the second law terms? Two things. How much air are we influencing, and how much are we deflecting that air? So when we think about the amount of air that we're influencing, it's like the wing influences a tube of air, and if you think about the amount of air that it's being influenced in a 1 second of flying, that the length of that tube will be based on our airspeed. If we're moving fast, it'll be a long tube. If we're moving short, it'll be a short tube. The width of that tube is largely based on our wingspan. If we have long wings, then we influence a wide tube of air. So those things influence the volume of air that we're influencing, and the air density will relate that volume to the mass of air that we are influencing. Second part of it is how much are we deflecting that air? The main thing that affects that is the angle of attack. When we're at a high angle of attack, we tend to be deflecting that air a pretty high angle. A low angle of attack, we're deflecting it only a little angle. The wing chord will influence how much time that the air is passing over the wing and how much opportunity the wing has to influence that air and deflect it. And also the airspeed, if something, it isn't influencing the angle so much, but if the air is moving fast, it takes a lot more force to deflect it by a certain angle. So the airspeed is changing the amount of force associated with a certain angle. So notice that the airspeed shows up twice in this list of factors that influence the magnitude. Turns out that the lift is proportional to the square of the airspeed. And since both wingspan and wing chord influence it, the product of wingspan and wing chord is the wing area. So the area of the wing will be directly related to the magnitude of the lift. Now let's move on to the Bernoulli's principle explanation of lift, which is going to approach the question from a different perspective. Bernoulli was a scientist a long time ago, and he observed something when he noticed a fluid flowing around objects. He noticed that the speed of the fluid would change as it moved around objects, And he measured the pressure and noticed that the pressure also changed as it moved around objects. And that kind of makes sense when you think about something has to be causing that fluid to speed up or slow down. And it is the pressure that does that. When fluid moves from an area of high pressure to low pressure, it speeds up because that pressure is pushing on it. Slows down if it's moving from an area of low pressure to an area of high pressure. Mathematically, the explanation of this, or the math that governs it, the pressure plus 1/2 of the density times the velocity squared is equal to a constant. This 1/2 density times velocity squared is called the dynamic pressure. The So the speed of the air relative to the wing, but outside of the influence of the wing, is what we call the free stream airspeed. And the speed of the pressure at this point away from the influence of the wing is the atmospheric pressure that we would measure, with a barometric pressure instrument. Those kind of determine what this constant is. So this equation is true for air along a path, or in a small area here around it. So as the air moves around the wing, some portion of the air is basically going to hit the front of the wing, and the air just above it will go around the top of the wing, and the air just below it will go around the bottom of the wing. Right near that point, which is called the separation point, the air comes almost to a stop. And it needs to come to a very slow speed because it's going to make a very sharp turn. And the air can't make sharp turns when it's moving really fast. So it does so the speed of the air right in this region here is almost zero. The air that's flowing over the top of the wing, it goes faster. Goes it travels a little bit farther distance than the air under the bottom of the wing. And to do that, it has to go faster. Since it's going faster than the free stream velocity, its pressure is lower than the atmospheric pressure. The air that flows under the bottom of the wing, it is a little bit slower than the free stream airspeed. And since it's a little bit slower, it has a little bit higher pressure than atmospheric pressure. This high pressure on the bottom of the wing and low pressure on the top of the wing create a net force upward on the wing. So when we think in the Bernoulli's principle explanation, how do we come up with the magnitude of the lift? Well, the equation for that is given here. It starts with the dynamic pressure, 1/2 rho v squared. The next term is the coefficient of lift, which is very closely related to angle of attack, and then the wing area. This graph shows the relationship between coefficient of lift and angle of attack. It's close to linear through the normal operating range of the glider. When you get up to too high of an angle of attack, this stalling angle of attack, or called the critical angle of attack, that's where the relationship stops being linear, and at some point more angle of attack actually reduces your coefficient of lift. Now this 1/2 rho v squared is called dynamic pressure. It's kind of convenient that that is what our airspeed indicator is actually measuring. It isn't measuring velocity directly, it's measuring dynamic pressure and converting that to a velocity. But in many ways, it's giving us a more useful measurement of our airspeed than if it was truly measuring our airspeed, because it's factoring in this density piece. So I'd like to talk a little bit more about induced drag. This picture kind of shows the situation at a relatively high speed where the wing is deflecting a lot of air by a relatively small angle. That the lift vector here, or the resultant force vector, is tipped back a little bit from relative wind, but not that much when we're at high speed, because we're only deflecting the air a small angle. When we are at low speed, what happens is, since we're influencing less air, we need to deflect that air by a bigger angle. That causes this the resultant force vector to be angled back or tipped back at a bigger angle from perpendicular relative to the relative wind. That makes the induced drag be a larger amount. So induced drag gets larger when we're operating at low speed and deflecting the air by a big angle than it is at high speed when we're deflecting the air only a small angle. So a few other things to know about induced drag is that long, thin wings will deflect more air than short, stubby wings, even if they have the same area. That's why gliders tend to have very long, thin wings. The ratio of the span to the chord is called the aspect ratio, and we want a high aspect ratio to produce less induced drag. Having these long, thin wings makes it a little bit structurally difficult for the aircraft designer to design the structure of the wing. But in a glider where induced drag is very important, it's worthwhile to face that challenge. Other types of aircraft where induced drag is less important because they can compensate for it by having a little bit bigger engine, they will do it differently, and they'll go with a shorter wing that's easier to make the structure good. Mathematically, a given amount of lift, the induced drag is inversely proportional to the square of the airspeed. Parasite drag is any kind of drag that is other than induced drag. It's basically the bad drag. There's three main sources. Form drag is basically how streamlined the thing is that's moving through the air. It's high for a blunt object, and it's low for a nice streamlined shape. And our gliders tend to be very streamlined shape when they are pointed in the same direction that they're moving, and when the air is moving over them kind of as intended by the designer. If we are flying uncoordinated, if we're not using the rudder to keep the airplane pointed in the same direction it's moving, then we're kind of making that glider fly sideways through the air, and the form drag goes up a lot in that situation. So skin friction drag is just drag due to the air having to flow over something that isn't perfectly smooth. For bumpy surfaces, the drag goes up. So when we have bugs on the leading edges of our wings or other parts of the aircraft, that makes the skin friction drag higher. Um, our better gliders have composite wings with nice smooth surfaces, whereas other aircraft use riveted wings or something that makes for a less smooth surface. One thing that really makes the skin friction drag high is frost. So if you're in a situation where frost has formed on your wing surfaces overnight, it's really important to get that frost melted off before going flying. Interference drag is drag when two parts come together at kind of a sharp angle. The most common example of this would be where the wing fits into the fuselage. There tends to be the air is being influenced by two different parts in a way that interferes with each other. That can be made better by having a fairing that makes the smooth interchange between those two surfaces. Um, that's extra effort for the designer, but it's worth it for very high performance. So parasite drag works the opposite of induced drag. Parasite drag is proportional to the airspeed squared. It gets higher as the airspeed goes up, a lot higher. So this is a graph indicating the induced drag is in blue here, which is decreasing with airspeed. Parasite drag is increasing with airspeed, and green is representing the sum of the two. So at a given weight, the total drag gets minimized at a particular speed. If we fly slower than that, the drag goes up because of our induced drag. If we go faster than that, our drag goes up because of increased parasite drag. This speed is the speed that will give us the best glide ratio, because the lift is basically going to always be related to the weight, but the drag changes. So the lift to drag ratio is minimized where the drag is minimized. Minimum sink speed actually is a little bit slower than the best L over D speed. So at minimum sink speed, you'll be sinking at a lower speed, but because you're going forward at a lower speed, you'll be actually sinking at a little bit higher angle. So what happens if we increase the weight? So when we increase the weight, our parasite drag didn't change, because the factors that influence parasite drag don't have anything to do with weight. But our induced drag goes up when we have higher drag or higher weight, because the wing needs to produce more lift. When the induced drag increases, the total drag increases, and it shifts up and it shifts a little bit to the right, so that the speed at which the minimum drag occurs goes up. So a heavier glider, if you take the same glider and you fly it at two different weights, the best glide speed is higher at the higher weight. That's why when you fly one of the training gliders with your instructor, the best glide speed is faster than when you fly that same glider solo. The best glide ratio doesn't change. Although the drag goes up, the lift also goes up, and they actually go up by the same amount or the same percentage between these two situations. So the glide ratio stays the same at higher weight. So induced drag is one byproduct of generating lift. Another byproduct is something called a wingtip vortex that makes when you think about the Bernoulli explanation of lift, you know there's high pressure air at the bottom of the wing and low pressure air at the top of the wing. And out here in the middle of the wing, the air can't flow from the bottom to the top because the wing's in the way. Out at the tip, there is a way for the air to flow from the high pressure area to the low pressure area, and that's exactly what it does. It goes around the wing at the wingtip. And the effect of that is that there's this circulating air behind the aircraft coming from its wingtips. That vortex it's going to be behind and it tends to flow down. It's deflected down just like the rest of the air that the wing is influencing. When you box the wake, you're encountering these wingtip vortices from the tow plane. Okay, now let's talk a little bit about stalls. So we're going to talk about what happens when we move out of this operating area region where the coefficient of lift increases steadily as we increase our angle of attack. We get to a point where the wing just isn't capable of deflecting that much air anymore. These pictures over here kind of show what happens. The air is, it sticks to the top surface of the wing nice when we're in this area of operation. When we try to make the wing deflect too much air, or deflect the air by too much, it can't make as sharp of a turn as it would need to. It separates from the top surface and starts just spinning around in a bunch of little teeny vortices here. The whole mechanism of producing lift kind of falls apart, and the lift drops off pretty rapidly as you increase the angle of attack past that. So the stalls don't necessarily progress the same across the whole wing at the same time. This picture here shows different wing shapes, and the way that the shaded area here indicates areas of the wing where the air is separating from the top surface of the wing at a point during the stall, and it differs for different shapes of wing. Ideally, you want it to happen so that the wing tips area where the ailerons are will be the last to stall, because that keeps your ailerons working well throughout the stall. But in some wing shapes, it doesn't tend to happen that way. So the aircraft designer can do some things about that. They can make the wings twisted a little bit so that the stall will progress nicely from the inside area out towards the wingspan. As a pilot, you don't need to have a real detailed knowledge of how wings are designed to influence this behavior. The important thing for you to know as a pilot is that different aircraft designs will have very different stall behavior. When the aircraft design training gliders, they put a lot of effort into making sure that they stall in a very benign way. When they design higher performance gliders, different criteria are more important than that. So the designer may not have done as much to make sure the stall behavior is nice and benign. So as you move past training and you start moving into higher and higher performance gliders, you are likely to encounter some that are a little bit less benign when they stall. Stalls always happen at a particular angle of attack, which is we call that the critical angle of attack, but they can occur at different speeds. Basically, anytime you're asking the wing to produce more lift, the stall will occur at a higher airspeed. Couple of things reasons why you may be asking the wing to produce more lift. One of them is if you put more weight in the aircraft, then the wing has to generate more lift to support it. Another thing is that when you are in a turn, you're using wing lift to create that sidewards force that causes the glider to turn. That means you need more lift total and your stall speed will increase. Also, the minimum sink speed and the best glide speed will increase. So this graph shows at different angles of bank what the percentage increase in stall speed is. It up through 30 degrees of bank, it's not that big, but when you get in to 60 degrees and more, it starts to go up very fast. So once the wings are stalled, increases in angle of attack decrease the lift. It's opposite to the normal behavior. And if your aircraft is rolling when the wings are stalled, the wing that's moving down has a higher angle of attack than the wing that's moving up. So it is generating even less lift, and less lift on that wing tends to accelerate the roll rate. So this is a very unstable situation where the lift on the two wings, the difference in lift on the two wings is causing more and more roll rate. It'll tend to continue rolling. Once that starts, the aircraft will tend to nose over and dive toward the ground, and you get into this fully developed spin situation where the nose is pointed almost straight down and the aircraft is rolling around. It doesn't tend to speed up a lot because it's a very high drag situation. Once you're in this spin, or basically any time that you're in a stalled situation, the ailerons tend not to be very ineffective. Sometimes they even work opposite, where moving the stick left will cause roll to the right. They're not an effective way at controlling roll. So the way that you normally get into a spin, either accidentally or if you're trying to do it on purpose, is a lot of yaw happening right near the time that the aircraft is entering the stall. So if you're trying to avoid spinning, you need to avoid having yaw as you stall. If you're intentionally trying to make it spin, then you would do the opposite. So the way to stop a spin is not what your intuition would tell you. People's intuition of what to do tends to be exactly opposite of the right thing, which is one thing that makes a spin very hazardous. When your aircraft is pointed straight at the ground, your intuition tells you you need to pull back on the stick to pull out of that. But actually what you need is you need to push the stick forward in order to reduce the angle of attack and get the aircraft out of the stalled condition. And then you need to use the rudder to stop the spinning motion. Your intuition is to use the ailerons, but they're not very effective. You have to use the rudder. Once you've recovered from the spin, then it's time to recover from the dive that you're in. So, in summary, the things that you really need to remember from this lesson is that in steady state, a glider is always descending with respect to the air around it. The reason that you can climb in a glider is because the air around the glider may be rising faster than what you're descending through it, and that allows you to climb. But relative to the air around you, you are descending. The blessed glide ratio doesn't change with weight, but the speed at which it occurs does change. Specifically, the heavier you are, the faster you need to fly to achieve the best glide ratio. The stall speed, the minimum sink speed, all increase with wing loading. Wing loading, it can be due to weight. It can also be due to pulling G's, like when you're in a steep turn. Up to a point, you can increase lift generated by the wing by pulling back on the stick and increasing the angle of attack. However, once you get to the critical angle of attack, then the lift drops off sharply in a stall. And if you have too much yaw as that happens, then you can develop into a spin.